Analytical Chemistry 1, Lesson 3. Much of analytical chemistry is about measurement. It is worth taking a little time to discuss where science is with respect to measurement. Anciently, measurements were based on some artifact. For example, in ancient Rome, the stride of a marching legionnaire, the distance when the same foot came down again, was used to determine distance. How far they marched was important. It was decided that 1,000 strides, now 1,000 mille, its variants are 1,000 in the various Romance languages, that would be how they kept track of distance. This 1,000 strides gave rise to the modern mile. You can see the word in it, mille, mile. One of Caesar's generals decided to further codify it. He used his own foot and measured 5 of his feet to be equal to 1 stride, so 5,000 feet became a mile. Things evolved over time, and in medieval England, it ended up with 5,280 feet being equal to a mile. Artifacts were used widely for measurement. In pre-revolutionary France, it's been estimated that more than 200,000 different measurement standards were being used. In each town hall, the mairie, an iron bar was cemented into the wall for the local aune, that's spelled A-U-N-E, used as the measuring standard for cloth. It dictated local commerce. Attempts at more standardization came, and a block of platinum-iridium alloy became the standard for the kilogram. Throughout the 20th century, scientists started to make precise measurements of certain physical constants of nature, such as the speed of light in a vacuum, for instance, and used these to refine and standardize these measurements. Many of the constants of nature would be measured and reported with ever-shrinking error limits as measurements improved. But finally, a different approach was agreed upon, and as of March 2019, the approach to measurement changed when the world's scientific measurement body that controls the Système International d'Unité, or SI units, defined 7 constants of nature exactly. Here are those defined values. The numbers given here do not have any more digits, even those written in scientific notation. These now are exact values. We may try to measure these values, and our efforts will have some uncertainty or error associated with them, but the constants themselves have no uncertainty or error. From these constants, we can combine them in various ways to derive the 7 base units that are defined by the SI system. For example, the property of distance or length is said to be measured by the meter. The speed of light, defined as being so many meters per second, and the frequency of an electronic transition in the cesium-133 atom, which is measured in reciprocal seconds, are combined to produce a definition of the meter based on these exact definitions. Time, mass, temperature, etc. are all derived from these defined constants of nature. And from these 7 base units, we are able to derive an unlimited number of units as needed. Now, 22 of these combinations are so common and have such historical significance that they've been given their own name. Other units remain very useful and important, but are given only in terms of combinations of these derived and/or base-named units. For example, the property of force has units of kilograms meters per second squared, but this combination of units has been given the name of the Newton and the symbol of capital N. The property of pressure has units of newtons per square meter, or kilograms per meter per second squared. It has been given the name of Pascal and the symbol capital PA. By contrast, the molar entropy change of a process, while it's a very important property to be able to measure, has not been given a separate name, and has the common units of joules per Kelvin mole, or in base units, kilogram meter squared per second squared per Kelvin per mole. There are some units which are not part of the SI system, but are so widely used and are of such a useful magnitude that their use with SI units has been approved. For volume, the appropriately sized SI unit for many things would be the cubic decimeter. However, the liter is defined equal to it, and its use is approved. One thing of note about the symbol for liter. We will see shortly that according to convention, its unit should be a lowercase l. However, in many fonts, the lowercase l is easily confused with the number 1. Because of that, an uppercase L is also approved for the symbol. Either one is acceptable. Try to be consistent. Personally, I prefer the use of the capital L. Consider now how to measure mass in the range that is useful for atoms and molecules. A century ago, chemists and physicists developed a measure for the atomic mass unit. Their definitions were not quite the same, but at first it didn't really make a difference. But as their measurement precision increased, it was clear that there needed to be an agreement, and a new definition was created and was called the unified atomic mass unit. It was given the symbol U. though many people continue to use the old AMU to mean the new definition. In more recent times, the Unified Atomic Mass Unit has been renamed the Dalton with the symbol capital DA. You will find people using U, AMU, and DA to all mean the same thing. DA is approved for use with SI and is particularly useful in the biomolecular field. Large proteins and other biomolecules have masses measured in kilodaltons, even megadaltons. Energy on the atomic scale is also nicely measured in a unit called electron volt. It's with the symbol EV. Chemical bond energies and molecular electronic excitations are readily measured with this energy unit. There are also some non-standard units that have not been approved for use with SI but are nevertheless still widely used. Pressure measured in atmospheres is an older measure but relates nicely to our everyday experience. While the symbol ATM is used widely in scientific work, the Pascal is increasing in the frequency of its use. The bar is another unit that is more directly related to the SI system, being defined as a nice multiple of the PA, and yet very close in magnitude to that of the atmosphere. Its use is kind of a trade-off between the two. A bar, whose symbol is also bar, is 100 kilopascals, compared to the atmosphere unit, which is 101.325 kilopascals. The SI system also has a collection of prefixes to scale any unit, so that large multipliers in scientific notation are not needed as often. The approved prefixes now cover a range of 48 orders of magnitude, from yocto at 10 to the minus 24 to yotta at 10 to the plus 24. Different fields of science end up covering this whole range and even beyond. You will become familiar with these over time. Note carefully the difference in the unit symbols. From yocto up to kilo, they are all lowercase. Beyond that, they are uppercase. One thing that was done many years ago, and you may see it if you read old journal articles, is that they combined prefixes before the new ones were defined. You might see a millimicro, well, now we would use nano, or micromicro, we now use pico. Resolving this was one of the motivations for standardizing these prefixes. Here are some basic rules about the SI units and their use. There are some name differences between American and international spellings. You will see both used. We tend to follow the international version, though both spellings creep in. Unit names are handled like any noun. They are lowercase unless starting a sentence or in a title. Unit symbols, however, are lowercase except when the unit name is derived from a person's name. Then the first letter is capitalized. Liter is the only exception, as mentioned earlier. A prefix is part of the symbol, so there's not a space between the prefix symbol and the unit symbol, and you never make a symbol into the plural, though if writing out the symbol name, you can make it plural as you would any noun. When multiplying units, a non-breaking space or a centered dot are both acceptable to represent their product. Division can be represented by a solidus, but never multiple solidus marks. It can lead to confusion and misinterpretation. It is better to use negative exponents. Group the digits of long numbers into groups of 3, but the suggested practice is to separate the groups with a space while retaining a period for the decimal point. This arises because of the different usage of commas and periods between Europe and America. This proposed scheme is meant to be a trade-off to improve clarity.